Okay, so the next carboxylic acid derivative we're going to look at are the amides. And I wanted to do preparation first, and then we'll go into the reactivity. So preparation of amides is pretty straightforward. The easiest method we've seen so far is simply to take an acid halide and then react that acid halide with some sort of amine. So this should be a review, and if you remember, the amine itself, this should be RNH2. The amine itself is going to act both as its nucleophile and base, so we're going to need excess amine. And when this happens, we can make a new amide bond where we have a nitrogen bonded to the carbonyl, and we can make a variety of different amides this way, depending on whether or not we're using ammonia, a primary amine, or a secondary amine. One of my favorite examples of this is by using the two reagents shown below. One of them is a diamine, where you've got two amines coming off of benzene, para to one another. And then our second reagent that we're going to use is an acid halide, where you have two acid halide groups that are para to one another. And as you can imagine, these two ends are going to stick together, but then this can continue going on in an infinite chain, assuming we have an unlimited amount of reagents. And by doing that, we can create a custom polymer. And this polymer, if we think about it, is going to have repeating blocks. So we can show it using the bracket notation, which I'll fill in a second here. And we're going to link these two groups together. In something that looks kind of like this. And so this will be our repeating unit. Looks like this, and the repeating unit can have, let's say, hundreds or thousands or hundreds of thousands of repeating units. This is actually how commercial Kevlar is made. And if you're unfamiliar with Kevlar, Kevlar is found in bulletproof vests, so the military uses them extensively. Police departments also use them as well. But one of the most interesting applications, in my opinion, is in spacecraft. A big problem that they have in space is the potential for a micrometeorite impact. So you can imagine on the International Space Station, you don't want a micrometeorite punching a hole through some sort of vital structure. So what they do in spacecraft is they actually wrap vital components in Kevlar, just in case a micrometeorite hits, there might be some chance of the Kevlar actually containing it, which is pretty neat. And the reason Kevlar is so powerful is this really, really strong amide bond. This amide bond is quite rugged, and it makes this a very, very strong polymer. All right, so let's take a look at the reactions of amides as well. And I guess before I go on, I did want to hit one important point. The method shown here is the only method shown in our textbook. However, if you go on and take more advanced chemistry courses, you'll see there's a wide variety of amide coupling reagents that are available. They're just not covered in our textbook, so I'm just going to cover acid halides exclusively during this lecture. All right, so the first reaction of amides that I did want to cover was acid hydrolysis. And this is one you actually already did in your pod without even realizing it. So in your problem of the day, one of your intermediates that you created was an amide. And if you have your amide floating around with water and catalytic acid under high temperature conditions, you can get a hydrolysis reaction to occur. So what occurs in the first step is protonation of our carbonyl. That makes this a really good electrophile. And then in your next step, water as a nucleophile can attack in to give you a tetrahedral intermediate. And this tetrahedral intermediate is then going to help us by doing a proton transfer, but let's go ahead and get this drawn out. So the water, when it adds in, has this extra proton on it. We eventually want to move this proton from that oxygen over to the nitrogen. So just to show this in a quick one-step fashion, I'm just going to write plus minus H plus, and we're going to move that proton from the oxygen to the nitrogen. And by doing that, we've created a really good leaving group, right? Because this nitrogen with a positive charge, if it falls off, becomes neutral. So we're going to go ahead and kick off this NH3 group, and we're almost there. Whoops. And we've got this NH3 that was kicked off as our leaving group. In the next step, this ammonia will actually help facilitate a proton transfer. So you can imagine in this next step, it's going to quickly get protonated by one of our acid sources. We can make our carboxylic acid and our ammonium ion in this case. So the ammonium ion is kind of trapped with that positive charge, but that's okay. We're actually able to just stick at the carboxylic acid, assuming we're under relatively low pH conditions for this reaction. So it's kind of neat that we can do acid hydrolysis with amides, but the one thing I did want to point out was that it did require this high temperature, right? Which is good, because if you think about the low pH in our stomach, we've got a lot of peptide bonds in our stomach. We don't necessarily want to rip those apart and hydrolyze out our proteins. So this does require relatively high temperature in order to take place. It doesn't occur at physiological temperatures, luckily for us. All right, the next one is kind of similar. It's base hydrolysis. And I'm not going to go over the mechanism just because it's kind of repetitive. And with base hydrolysis, as you can imagine, instead of using acid, we're just going to use some sort of base. So we're going to have NH2. And just like before, if we use base in and of itself isn't enough. We also need to apply a fair amount of heat in order to rip apart that amide bond. And at the end, we need to ensure that our carboxylic acid is protonated by treating it with a second step of an acid wash. So we're actually able to convert this to a carboxylic acid as well. All right, the last one I wanted to show you is the reduction. And the reduction one is kind of unique. The textbook doesn't show the full mechanism. So we're just going to stick with showing you the overall transformation. And as you can see, this kind of looks like an ester. The only difference here is we have a nitrogen instead of an oxygen, and this implies that we need a strong reducing agent. The strong reducing agent that we know of is LAH, and again, we're going to use this in excess, and we're going to hit this at the end with the dilute acid to ensure that our product is protonated. All right, in this case, instead of getting an alcohol, what's interesting is you end up getting an amine. All right, so it's a little bit tricky. Often students are tempted to show an alcohol as the product, but try to remember when you reduce an amide, you always get the amine. Okay, so before we wrap up, let's just go ahead and draw our brief reaction map. And since we're getting down to the less reactive carboxylic acid derivatives, it's going to be a bit smaller. And what we'll do is we'll show an acid halide on the right. We'll show an amide in the middle. I'm just going to make it a simple amide. We'll do a carboxylic acid over here. We'll do an amine over here. And we'll do a nitrile over here. We didn't see the nitrile reaction in this video, but in our next video when we cover nitriles, we'll actually see this reaction. But for right now, we'll just throw it in. And we can make an amide by reacting an acid halide with ammonia or some sort of amine in excess. It's important to remember you need more than one equivalent. And we can convert an amine to a carboxylic acid one of two different ways. The first way is just to treat this with acid and water under high temp conditions. The second method is to treat it with NaOH and heat, followed by an acid workup. Both of those can be used. The main feature, like I said, is we need to apply a fair amount of heat in order to break that amide bond. It's quite stable. And if we want to form a primary amine, in this case, we need to do a reduction reaction. So we're going to use LAH in excess, followed by some sort of proton transfer. It could be aqueous, acid, or just water. And then the last one that we'll see in our next video is how to convert an amide to a nitrile. This is actually done using SOCl2. That's our thionyl chloride reagent. That's the reagent, if you remember, that we could also use to make this backwards transformation. So we could use SOCl2 here. Thionyl chloride is a really powerful reagent, and in this context, it doesn't change anything into a chlorine in our final product, but it can help us to convert this product eventually to a nitrile. All right, so that's where we'll stop here. When we come back, we'll finish up by talking about nitriles.